What do you do with a balanced equation? How does that fit into determinations of heat transfer during the reaction? We'll go back to this is propane, right? Same stuff you burn in your grill. And this, oops. This value is the amount of heat in kilojoules that is evolved during this reaction. And like I said last time, in this case, it's given to you as per mole of propane. So for every mole of propane in this reaction, you get that many kilojoules out because it's a negative value. Right? Negative means exothermic. If you need to use the reaction for some other calculation, then you substitute in here so many moles of one of the others, like 5 moles of oxygen, or 3 moles of carbon dioxide, or 4 moles of water. And that will prorate it by moles based on these other factors. But since there's only 1 mole of propane, then this value is for the entire reaction. Okay, so calculate the delta H in which 5 grams of propane is burned in excess oxygen at constant pressure. I guess I better write the equation up here. I'm going to leave the phases out for compactness. And this is like any other equation. You can't do anything with it unless it's, unless the equation is balanced. We can check ourselves and we'll find that it is balanced. But what we're given is, now we're dipping our toes in the stoichiometry pool again. This is given as 5 grams. And oxygen is excess. So that removes one problem. We don't have to see which one runs out first. This one's going to run out. And then the amount of heat, and delta H is what value? Remember, Q is heat. Q is actual heat transfer between 2 objects, 2 substances, 2 regions that are at different temperature. Delta H is enthalpy. This is the potential heat that can be generated from this reaction. And that's minus 2,221 kilojoules. Okay. If there's nothing here in the denominator, in this case, we do have something in the denominator per mole of propane. There's nothing in the denominator. Assume that the value is for the reaction as written when balanced. Right? And that would be in terms of moles. The only time you have to consider the denominator otherwise is if this value is actually given in kilojoules per gram or kilojoules per liter of some gas that's in the reaction. Otherwise, assume that it's in terms of moles and the entire reaction. Okay. In this case, it's per mole of that. So naturally, we need to figure out how many moles of propane this represents. We need to find that magic number, right? Molar mass. So we're going to do 3 times 12.01 for carbon and 8 times 1.01 for hydrogen. And 12.01 times, and so that's 4411 grams per mole. And so now this is the dimensional analysis part of the problem. Actually, it's one of the dimensional analysis parts. Grams has to go on bottom. Right? So this one will cancel out, leave us with moles. So this tells us how many moles of propane is burned in this reaction. Let's see. And I get 0.1134 moles of propane. Okay, so now we're going to take this value, kilojoules, and we can say this is where you insert the denominator based on which, if we had been, if the problem had been written in such a way that we say, all right, how many kilojoules would be expended if we produce so many grams of water? Then you would convert that to moles and you would put, this is per 4 moles of water. But in our case, we want it as per mole of propane. Is that connecting? Okay. Otherwise, the dimensional analysis just doesn't work out right. So for every 1 mole of propane, excuse me, how many moles of propane? 0.1134. This way, the moles cancel and leaves us with kilojoules. All right, so 2221, and that's a negative. Let's see. Since this is a conversion factor, it's an exact number. This one is the one that determines the number of significant figures. 0.18 kilojoules. That's the heat that's evolved from this reaction if we burn 5 grams. Oops. Oh, I did read it wrong. $252 kilojoules. Okay, think you can work a problem like that? With practice. Okay. So, how do we get the information from a reaction that we want to study in the lab? It's a process called calorimetry. Calor meaning heat, and metry comes from to measure. So we're just actually measuring the heat. But do we have the ability to directly measure heat that's evolved in a reaction? We don't have anything in our lab that will measure joules, at least not in this lab. So we have to get the information indirectly. What does that mean? We have to measure temperature differences. Temperature differences and other factors together will tell us how much heat is being transferred in a process. So in order to know that, there are some values that are important for us that are specific for each substance. It's called specific heat capacity. Now, if you have an object here, and it's say at 70 degrees C, and you allow the heat to equalize between some other object here that's at 0 degrees C, which way is the heat going to move? Right. That way. And we'll see a difference in temperature, right? This one will start at 70, this one will start at 0. This one will equilibrate at somewhere in between the two. This one will get higher, this one will get lower. But it's a characteristic of mass, of matter, that this matter won't behave the same as that one unless it's made from exactly the same stuff. If it's made from something different, like say this is water, and this is iron. At that temperature, and with the temperature change, a certain amount of heat will be transferred. But water will get all of that heat transferred, but its temperature won't change the same as this one. Say this one goes from 70 to 50. Then this side won't go from 0 to 20. Same difference. And the reason that they're that way is because they have, well, actually, it's internal characteristics of matter. And the way we get a handle on that is specific heat capacity. So what do we mean by specific heat capacity? Well, it's a number. It's the amount of energy that's required to raise the temperature of 1 gram. Temperature 1 degree centigrade for each gram of substance. And that is characteristic of the substance. So if you have pure iron and you determine a value here for that, and you get another sample of pure iron, then it will have exactly the same specific heat capacity. And I don't know what that is off the top of my head, but we give it a variable, a letter, C, in our formulas. Okay. Now, that's if we're measuring the amount of heat it takes to raise the temperature 1 degree for every gram. But if we're talking in terms of moles, instead of specific heat capacity, we're talking about molar heat capacity. And all you have to do is change this value here, right there, per mole. And sometimes there'll be a subscript for that C that'll tell you what it is, and sometimes it won't. But the formula doesn't change. Okay. All right. Let's do this. Is sort of trying to develop some intuition about calorimetry. If you have 2 reactants separated, and then you put them together, and they're both in solution, and and you measure the temperature. Say it's a slow reaction for our benefit. You measure the temperature when you put them together, and then you measure it 10 minutes later, and the temperature is higher. That implies that the reaction is exothermic. It gives off heat. If the reaction mixture gets cooler, then it's endothermic. Oh, Professor Dave again.
Hey, it's Professor Dave. Let's talk about calorimetry.
He knows a lot about the science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water, and the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. It occurred to me that we're going to need to, rather than subscripts of that C, what we're going to call C is the heat capacity of any substance. And what we're going to call S is the specific heat capacity. Okay, so what's the difference? Heat capacity is an extensive property. In other words, it changes with the amount of substance. So if you have more substance, it'll be able to absorb more heat for the same temperature change. Okay, so this would be in terms of joules per gram of substance, whereas this one would be joules, since it's an intensity factor or an intensive property, it would be in terms of degrees C per gram. Okay, so that I was just checking your lab experiment, and it does use this convention. C is the heat capacity, S is the specific heat capacity of the substance. So we'll stick with that convention. Okay, so why would we want to use either one of these? Well, in this particular case, if we're trying to identify a substance like that piece of metal, then this would be more valuable because it won't change with how much metal you have. But for this one, we use this one in situations where we have no control over the amount of something, and we just need to find that value for whatever we have, and that is is calorimeter. If you have a different thermometer put in there, if you have a different stir, if you have a different set of cups, then this value is going to be different. And that's why the first 2 pages of the procedure, well, after the pre-lab questions, is a procedure on how to find the calorimeter constant, is the name we're giving it, but it's the heat capacity of the calorimeter. Okay. We need to know that, because, and I'm going to show you. Professor Day was following the convention that I was taught in school, and I never did like it then, but I did what I was told. Now I can give you a better way, a more logical way to determine those values, unknowns in the calculation, and I'll show you in just a second. We're going to use 2 styrofoam cups. And we're going to use a thermometer, and we're going to have a solution in here. It'll either be pure water if we're going to drop an object into it, or it could be 2 solutions that we add together to react. We're going to have an acid-base reaction, okay, in that case. But I'm pretty sure we're going to eliminate the stir, because the stir, you need to stir your solution. That's true. I mean, it needs to be equilibrated. But the stir creates more problems than it's worth. The material I use for the stir, if it stays in the solution, say it's acid or basic solutions too long, it corrodes, right? And that affects your outcome. So what we're going to do is be careful, and we're going to use this thermometer and stir it with the thermometer. Okay. Now, going back to what I described in our in part 1. Remember, if you have a system where both matter and energy can cross the barrier with the surroundings, it's an open system. If only energy can cross the barrier, it's a closed system. No matter can cross. And if we eliminate both matter transfer and energy transfer, we have an isolated system. This is an isolated system, this calorimeter. We're treating it as an isolated system because we're going to have 2 coffee cups together, and that will prevent over the short term any substantial transfer of energy or matter, for that matter, between the outside, the surroundings, and the system. And that's important. And I'll show you why mathematically in just a second. Okay. What that does for us is any heat that transfers inside that calorimeter in between anything. It may go between the thermometer and the solution, or it may go between 2 solutions that are actually mixed. So we have to sort of imagine that they're separate solutions, but the summation of all the heat transfers in that isolated system has to be 0. So I write it this way. So there's one process. We measure the heat transfer for this process inside the calorimeter. And then we can mathematically separate out a second process. And then say we have a third process that we are able to get a handle on. And this can go on as far as you want it to. Then all you need is, what is this? How do we get at each one of these? But they all have to add up to 0. And that's why the sign is extremely important. Is it positive or negative? Okay. Let's see. Okay, here's our calculation. All right, let's say we drop the metal in, and the metal is at, let's make a table over here. Let's say the temperature of the metal is equal to 100 degrees. Right? We have it in boiling water. The temperature of the water that we're going to drop it into is room temperature. I'm going to say 20 degrees. We like to keep our room cooler. That's before we put them together. After we put them together, the temperature at equilibrium is, I don't know, say 40 degrees. Okay, so this one had a decrease at equilibrium now. These both metal and water are at the same temperature. So this would be the final temperature for each process. And the water process would start here. This is initial temperature. This is the initial temperature for the metal. This is the final temperature for both of them. Okay. Now we know the temperature transfers. What we need now is which formula to use. Well, for now, we're going to assume that the calorimeter has no effect, just for argument's sake. So we really only have two terms here to deal with. One for the metal and one for the water. Okay. So this one, do we know the mass of the metal? Well, yeah, let's say we do. Mass of the metal is, say, 60 grams. What's the mass of the water? Well, we normally don't measure mass of water, we normally measure volume. Well, as it turns out, at that temperature, water is 1 gram per milliliter, like very close to it. So let's say we have 100 milliliters of water in our container. So the mass of water is equal to 100 grams. 1 gram per milliliter, we have 100 milliliters, 100 grams. Okay. So the formula we're going to use here is this one is equal to the specific heat of the metal times the mass of the metal. Be consistent. There we go. Times the change in temperature. Now, is that going to work? Let's look at the units of measure. What is this? This is joules per degree C gram. This is in grams. This is in degrees C. They cancel. These are with joules. So our units confirm that we're, at least as far as that goes, we have all the terms we need. And then we're going to add the specific heat of water times the mass of the water times the temperature change of the water. Yeah. There we go. Right? And all of this should be equal to 0. Okay? I'm not doing more work than I need to. I'm sort of getting ahead of myself, but that's okay. That means the subsequent slides, we can breeze through them pretty quick. All right, so in this case, this isolated system says that that value is 0. Now, what do we have here? Well, we don't know what that is. Right? It's not given to us. The specific heat of the metal is unknown. But we do know the mass, right? 60 grams. How about the temperature? Well, remember, anytime you have a delta and you have to calculate a difference, it's the final minus the initial. So the final temperature is 40 degrees for the metal. And the initial temperature is 100. Okay. All right. So now we have the water. Well, the specific heat for water, we need to know that. Otherwise, we have two unknowns and we can't solve the equation. So we need to know the specific heat of water. And I think it's 4.18 something. I believe it's here in the method. 4.184. Joules per degree C gram. Okay. And we do have to be careful about our units of measure. Sometimes they'll slide a kilojoule in there, so watch out for those. All right, so in this case, the water then is going to be 4.184 joules per gram degree C. Like that's usually the way it's written. And then the mass of the water is 100 grams. And what's the change in temperature? Well, the final, which is 40, minus the initial, which for water is 20 degrees C. Okay? So now all you have to do is use a little algebra and solve for that unknown. Okay, do we need to do that? I just kind of made it up on the spot. I don't even know if it's real. Okay, so let's do all of this one. 40 minus 20 is 20, right? It's a positive 20 times 100 times 4.184. So that's 8,368. 8,368 joules for the water. Now for this one, 40 minus 100 is minus 60, right? So we have to use a minus 60 times 60 times our unknown. So this is minus, I'm going to use scientific notation, 5.071 times 10 to the 7th S M. So this is times that. And that's all equal to 0. Okay. So notice if we take this one, put it on this side, it becomes positive. Right? Okay. So I'm going to do 2 steps at once. If this goes on that side, it's this times that is equal to that. So this stays over here, and we divide that by this number. So it's, wait a minute, I did something wrong. Yeah, I did something extremely wrong in my calculator. So let me do this one again. 60. Oops. 60. Let's change the sign on 60. So this should be negative. 60 times that. That's more like it. Minus 3600. There we go. So now, okay, just didn't seem right. 10 to the 7th. I had left that number in there when I did the multiplier and multiplied by that again. That's what happened. Okay, so we bring that over here. Now this stays on this side, and that becomes the divisor of that. So 8368. Let's see, I'm going to have to swap the. Yes. So I get 2.32. All right, so what are the units of measure? Well, specific heat capacity is joules per gram degree C, 2.32. Most metals are less than 1 until you get up here in this heavier ones, then you get some really high heat capacities. But most metals have a heat capacity that's less than water. Well, this one is less than water, but not a lot. Okay. So what would we do if we had to incorporate the calorimeter into this calculation? It would be another term. Right? So what would this be equal to? Well, when we're talking about heat capacity and non-specific heat capacity, all you need to know is the calorimeter constant times the change in temperature. You don't even have to know the mass. But when you're doing your experiment, Once you determine that value for your calorimeter, you can't change anything about that calorimeter. Like if you poke a hole accidentally through one of the cups and have to replace it, you gotta start over. Because the calorimeter is an extensive property. In other words, you change anything about the matter, the mass, and it changes that value. So this is going to be joules per degree C. No, excuse me, yeah, degree C. And then the temperature change would be, well, we don't know. But it's usually, this temperature change is usually the same as the water, right? Because before you put the metal in it, the calorimeter is at the same temperature as the water. So this would be in another 20 degrees C. But what we don't know is that value. That's why you have to determine that first before you do the rest of the experiments. Okay. I don't like that eraser. It's too slow. I thought my WD-40 would fix this, but I think the longer that marker stays on the board, the harder it is to get off. Water? Yeah, this is water. Whoa, whoa. It's a broken device. Oh, just unscrewed. Somebody's been playing like salt shakers at the restaurant. Loosen the cap so the next person that picks it up spills it all over their food. Now this thing's busted. Have to get a new one. Yeah, that much better. Moisten it up a little bit. There used to be a kitchen cleaning solution that Clorox made. It's called Greenworks. Remember that one? They came in a bottle that had the siphon built in to the side of the bottle. It was great. I loved it. And then it just disappeared one day. I don't know what happened. Maybe the EPA got hold of it. Okay. So where was I? There we go. Right, mass change in temperature, final minus initial, always the order of things. And there's your generic calculation. Every heat transfer inside your isolated system has to add up to 0. We'll go through this one pretty quick. Say you have 100 grams of water at 90 degrees and 100 grams of water at 10 degrees. When you put them together, what's the temperature going to be? Well, since they're the same substance and the same mass, then they should absorb or release heat in the same amount, as the case may be. So this one, they're going to meet in the middle. This one's 90, that one's 100, right? So they're going to meet at 50. 10 plus 40 or 90 minus 40. So it should be B. Okay, that was easy. What if we have 100 grams of water at 90 degrees and 500 grams of water at 10 degrees? We can reason that out, say, is it exactly 50? I don't think so. Because you got more water at the lower temperature. So it's going to be lower, it's going to be less than 50 degrees. Right. And we go through that same process. Set up water as one of the waters, the hot water is QH and the other one is QC for cold. Do those calculations for each one. And what would the unknown value be? The unknown value would be the final temperature, right? So it would be one of them, say hot, let's just do that. Q hot and would be, well, it's this one plus this one. Q hot would be S mass of hot, and change in temperature would be final minus initial. So the hot one would be what, 90 degrees. Okay, this would be 4.184. And this one would be 100 grams. Okay, so there's your unknown. You're gonna have that same unknown in the second term. It'll just be final temperature minus initial temperature, which was, oh, excuse me. Yes, that's right. Minus 10 degrees. This is the initial temperature for the first one. The initial temperature for the second one is 10 degrees. And this value would be 500. That value would be the same. Then you just solve the unknown. And if you do all that stuff, it's going to be 23 degrees, which confirms that we thought the temperature would be between 10 and 50. It is. Erase it before it sets in. Okay. I'm doing on time. About a half hour. I think we've got another Professor Dave coming up right after this one. Okay, now in this case, we've got 50 grams of water at 10 degrees and another different substance altogether, 50-gram iron ball at 90 degrees. And we want to know the final temperature. In this case, we've got a similar situation where we have Q1 and Q2, or Q iron and Q water, but we have different specific heat capacities. So those terms will be different in that calculation, but we'll still be looking for that final temperature, right? And if we do the calculations, we find out the temperature is actually between 10 and 50. Even though we had the same mass of each one, the heat capacity of the iron was about 1/10 of that of the water. So its temperature will change with just a little bit of heat. And that's characteristic of water. Water has a very high heat capacity for its composition, for its formula. Okay, so it's actually 18 degrees. Just do that calculation. Now, if you actually want to see this done, I think one of my previous semesters, I've got it, took time and did it. Okay, now, this goes back, Hess's law. This goes back to the fact that enthalpy is a state function. In other words, it just depends on what your beginning state, what your end state, the path in between doesn't matter. And Hess's law just says that if we have a reaction here, say A plus B yields C plus D, and we want to know what's the enthalpy of that reaction, but we don't want to perform that reaction. Maybe it's too expensive. Maybe it's potentially hazardous, right? It could be extremely exothermic. So we want to do the calculations ahead of time to see if we need to take special precautions, right? Is it going to explode in our face? Well, Hess's law says if we know any number of other equations and they have their heat capacities here, we know those values. And we can manipulate these equations in some way so that we can add them together and equal that equation. Then we can use these values to find out what that one is. And the only reason we can do that is because this is a state function. It doesn't matter how we got there, right? Well, just beginning and end. That's all you need to know. Sometimes these are called steps, but that's a little misleading because steps implies that these reactions occur, and this one occurs, and that one occurs, and that one occurs to get there. But that's not it. This is purely theoretical, jumping through hoops to get to this one. It'll make more sense once we try a real one. Okay. All right. Professor Dave is going to try to explain Hess's law. Let's see if he does a better job.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are two ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite, so let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right, where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope, or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. You went a little bit further than I've gone up to this point, but I will explain. First of all, let's take an example of Hess's law. Say we're interested in this equation where nitrogen gas is reacting with oxygen gas and gives us 2 moles of nitrogen dioxide. Now this particular, let's see. Oh, this is the overall equation, okay? So we're saying this is the value for that, the enthalpy value for that equation. And notice they don't put any units here in the denominator. So this will be 68 kilojoules for every mole of nitrogen, or 68 kilojoules for every 2 moles of oxygen, or every 2 moles of nitrogen dioxide. But this equation can also be broken down into these 2 possibilities. You have nitrogen plus 1 mole of oxygen yields 2 moles of nitrogen monoxide with that value. So this is an endothermic reaction. That's a positive value. This is endothermic, right? All positive values for enthalpy are always endothermic. Negative values are exothermic. And this one, where we have 2 nitrogen monoxide plus 1 mole of oxygen yields 2 nitrogen dioxide, is exothermic. And is it written correctly though? Right? There's 1 nitrogen, there's 2 oxygens, there's 2 nitrogen monoxides on that side and 2 on that side, which means they cancel. And then we have 2 nitrogen dioxides. Okay, so with these values associated with those equations, we can add these together, get that equation, add these together, and we should get that value. Okay. So we could have not known this value and just said, okay, we know this one, we know that one, and we know that when we add them together, we get the target equation. Then when we add these together, we know we get the exact value, and that would be put in here. Okay, this is just a diagram of why Hess's law works. On the left, we've got those 2 steps that we went through. We went from here to here in the first equation, and then we went from here to here in the second. So this is endothermic, this is exothermic, and we end up at the same place as if we had conducted the target equation, that reaction, independent. So you get the same values. Okay, Professor Dave mentioned rules. If you're going to add equations together and use Hess's law, the equations that you eventually add together must give you the target equation. But you can take the component equations and manipulate them. You can either reverse them. If it's necessary to reverse the equation, then you just change the sign on the delta H. But what if that's not enough? Say that equation needs to be multiplied by a value. It needs to be increased by 2 or 3 or 4 times, or even take a half of it. That's possible. When you do that, then you recognize that the enthalpy is directly proportional to the moles of substance in your equation, and that's based upon coefficients. So if we cut the equation in half, delta H gets cut in half. Okay. So here are two equations that are, these are true equations. Notice though that we're using 1/2 here and 3/2 here to give us this 1 mole here. I know when we first started, we wanted whole number coefficients, but you don't have to have that. And I'm going to show you after Hess's law, the heats of formation, how we do heats of formation, and nearly always heats of formation, you have to include fractional coefficients. So we can't think of these in terms of individual atoms or molecules. We have to think of them in terms of moles. But you can't have a 1/2 a molecule. You can have a 1/2 a mole, yeah. If you change your mindset to moles, then it works out. But this one is endothermic, 46 kilojoules for 1 mole of ammonia. And this one is minus 484 kilojoules, which is exothermic for 1 mole of oxygen, excuse me, wrong way, 1 mole of oxygen or 2 moles of hydrogen to yield 2 moles of water. So this is for the entire equation, and the denominator is whatever you want it to be based on the balanced equation. All right, so we're going to use that information, and we're going to see, can we combine these two and make that one? Well, let's look. We need nitrogen. We got nitrogen up here? Yeah, there's nitrogen. Water, we've got water here. Oxygen, we got oxygen there. Ammonia, we got ammonia there. The one thing you don't have down here is hydrogen. So we're going to have to combine these in such a way that the hydrogens cancel. And we have to put things on the right side. Notice that ammonia is on the wrong side of the equation here. It needs to be over there. And it needs to be more of them. And water needs to be on this side. So we're going to flip this equation and put ammonia on the right, nitrogen on the left, and flip this equation and put oxygen on the right and water on the left. So we got to flip the equations, which changes the sign of enthalpy. And we have to multiply at least one of them by a factor. Right? So the best way to solve these problems is to work backwards. What's your target equation first? Because I might just be sneaky enough to say, I want you to find the enthalpy for this equation, right? And I'm going to give you 6 different equations that need to be combined. Well, if you look up here and say, I need this one, this one, this one, and you look down here and say, okay, that one's got what I need, that one's got what I need, that one does, that one doesn't. That doesn't mean you don't use that missing one. It means you look to see, are there factors in these others that need to be canceled with that third one? Sometimes there's an equation that goes in there and its sole purpose is to cancel other factors. Okay, so you work backwards from the target equation. You're reversing the equations that need to put terms on opposite side of where they originally are, and you change the sign of the enthalpy. And then you multiply reactions by a factor. Could be a fraction, could be a whole number. All right, so in this case, we start off with these two. There's the desired equation. Multiply the reactions to give the correct number of reactants. Okay, so we had to multiply to give us the correct number of, well, we had to reverse the reactions. Yeah. So that's not correct. We reversed it first. We make a note of that. Reverse. Okay. Oh, that was on a previous slide, wasn't it? Did I go too fast? There it is. I must have hit the button twice. So reverse the reactions first, then multiply by a factor to give you the correct number of terms. And then check to see if they add together correctly, and then cancel things that you can cancel. And check to be sure that you've got the right numbers of each one down here, there, there. Then, and at the same time, you're keeping track of your enthalpies, changing signs, multiplying by your factors. Then you can add them together. And this reaction should be endothermic to the tune of 1268 kilojoules. So it's going to get really cold. Okay, standard enthalpies of formation. The standard enthalpy of formation is a unique number for each compound. And I say compound because elements in their standard states don't have enthalpies of formation. They're, by convention, they're zero. So this one would not have an enthalpy of formation. That one would not have an enthalpy of formation. Any of the diatomics would not have enthalpies of formation, or any elements, right? Or any elements do not have non-zero values. So what do we mean by standard enthalpy formation? Well, we need standard conditions, right? And for these reactions, remember gases were a little bit different. I kind of gave you a heads up there. Standard temperature is 25 degrees C. Standard pressure is 1 atmosphere. And if you have any solutions that are involved, the concentration has to be 1 molar. Did we do that on the solutions? Concentrations? We did here. Yeah, we did. So, well, molarity has to be 1 molar. Okay, now that we have those conditions, then we have to define how do we write a standard enthalpy of formation. You need the equation first, right? If you're just looking in a reference manual and it has a list of compounds and says over here, delta T 0 sub F, right? It doesn't show you the equation that got you there most of the time. So you need to be able to write the equation. So on this side, you write the compound. Say our compound is water. 1 mole of that compound is on this side. That's fixed. Can't change it. So how did you get there? You used elements in their standard states. Right? Use hydrogen and oxygen in their standard states. And at that temperature, this is a liquid. Okay? Then you balance the equation with coefficients over here without changing that one. That's why we need fractions so often. So how many oxygens do you need? 1. Okay. How many hydrogens do you need? 2. That's it. That's the equation that you would associate with a standard heat of formation for water. Okay. This doesn't help you. Let me skip that. We never saw that. I snuck a slide in here that didn't need to be there. Okay, so Professor Dave's little talk produced an equation. Delta H for the reaction is equal to sigma. Does anybody know what a sigma means? It's a term that we use for summation. You add up all of these terms that are in the product side. And in order to do that, you have to take into account the number of moles of each one. So you need standard heats of formation of each of the compounds times what's the coefficient. in your, not this equation, but in the equation, your target equation. So you add up all those in the products. And then you subtract the summation in the reactants. Okay. And if you have an equation for a reaction that's balanced, and you're given a series of equations that you can add together using Hess's law, you'll get a value for delta H. If you take that same equation and you use standard enthalpies of formation, you get the exact same value. So this is very convenient. Notice that in this one, we have the standard heats of formation. That's an element 0. That's an element 0 in its most stable state at 1 atmosphere pressure and 25 degrees. So in this case, you only need a value for that one and a value for this one. So you say 2 times the value of this one here minus 2 times the value of this one here, and add them together and keep the signs. You should get minus 368 kilojoules from that equation. So it's exothermic. All right. There are, or should be, several problems using both Hess's law and the standard heats of formation in that review document. So it'll give you practice. And next Tuesday, we'll review. Okay, just a few words. Yeah, I got a couple of minutes. Just a few words on sources of energy. I'll try not to get preachy. Fossil fuels. When we say fossil fuels, think fossil means in the ground. Something has been fossilized. Think of petrified forest in, where is it, New Mexico? You find all these tree trunks laying around, you go up and bang on them, and they're solid rock. They've been fossilized. So any fuel that comes from the ground is a fossil fuel. Any petroleum product like oil, natural gas, coal, any of those are fossil fuels. I'm not sure if they include very poor quality things like peat that they use in Ireland and Scotland. Sometimes I think they use them. They use that material to make the whiskey. I think it makes it taste better or something. So other sources of energy, wood. For the longest time, wood was our primary source of energy as a civilization until we cut down on forests. And then we had to look for something else. So that's when we turned to fossil fuels. From wood to fossil fuels. First it was coal, primarily. Then oil and natural gas came along almost at the same time. Because usually when you tap oil reservoir, there's going to be some natural gas in there. At first they just flared it off. They burned it off. They didn't care about it. And they're still doing it in some places. If you can't get that gas out and send it someplace, then just burn it off because it's a nuisance. Other sources of energy, hydroelectric power. In order to use hydroelectric power, you need a potential energy difference between water at one place and water at another place, and that means height. So this positional potential energy of water determines how much energy you can get out of each liter of water that flows through your turbines. And most turbine designs require that you have a certain amount of pressure, head pressure, in order to make them work. The problem with hydroelectric power is there's only so much fresh water on the planet in the proper location that you could build a dam and create a reservoir that will drive generators. So, and we're pretty much at the limit now. Nuclear power. Nuclear power is derived from changes that occur in the nucleus of one element as it changes to a different element. And there are two types of nuclear power: fission and fusion. Fission nuclear power, you take a heavy, unstable element in proper concentration and it splits. And when it does, you have one element over here, you have one atom over here, and it yields two different atoms, say A and B. They're different elements. The mass here, the mass of X, is greater than the mass of A plus the mass of B. Okay, so you lost mass in this transition. Where did that mass go? It went where Einstein said it would go. Mass is converted into energy. That's nuclear power from fission. Fusion, you take usually two lighter elements, like isotopes of hydrogen. Let's see. I like deuterium and wait, that's not deuterium. Yeah, it's deuterium. And tritium. And you combine those two together and you get helium. Plus some neutrons, I think. So that would be 5 nucleons for +1. Okay, so that part balances. Okay, similarly, the mass of these two, the mass of reactants and the mass of products, says that the mass here is greater than the mass there. And that difference in mass is again converted into energy. That's nuclear power, either way you do it. Fission is easier. Fission just happens. That's why the nuclear power plant that's based on fission can run away from it, because it will happen no matter what you do. If you remove the control rods that are moderating the flow, the bombardment of neutrons on this element, and lose control, then the neutrons become plentiful, they break down a lot, it gets hotter and hotter and hotter, and China syndrome. It burns a hole through the planet all the way to China. Not really, but that's what we're saying. So that one, you can lose control of the fission reaction. But a fusion reaction is very difficult to produce outside of the sun or outside of stars. And if you're not constantly feeding energy in to make the reaction go, then it'll shut down. So it's a negative feedback. This is positive feedback. Okay, only got a couple minutes. This just shows the trend from wood, right? Wood disappeared, and these are the years, right? Wood disappeared virtually overnight. There's still some people use wood, not on an industrial scale. And then we picked up with coal first, and then petroleum and natural gas took over. Hydropower and nuclear power kind of peaked in the 70s until the greenies got hold of it and decided that that was their cause. You know, destroy nuclear power. The rest of the world be damned. And by the way, if you have anybody that's standing up in your face and arguing with you about global warming or global climate change, and they're talking about carbon dioxide emissions and all these gases we're putting in the air because of burning fossil fuels, ask them what their position is on nuclear power. If they're against nuclear power, then you have my permission to call them a liar. Because anybody that supports greenhouse gas and as the cause of global warming, would just jump at the chance to use nuclear because there are no carbon dioxide emissions at all. There's just waste heat that you have to get rid of, and any power plant has waste heat. So if they're against nuclear power too, then they're frauds. Okay. This one blurb on Earth's atmosphere. Carbon dioxide, truth be known, has very, very little impact on the greenhouse effect. At the levels we have it here, like around 400 or less parts per million of carbon dioxide in the atmosphere, that's not enough to cause any problem. There are other gases that are much more strongly absorbing of infrared radiation to keep it from going back into space. Water vapor. Now, water vapor is not as efficient as carbon dioxide for absorbing infrared radiation, but there's a whole lot more of it. Right? There are other gases that are even more effective than carbon dioxide. Methane. Right? So that's why they want to stop cows from belching. They turn loose methane. Besides, if we didn't have some sort of greenhouse effect at some level, then this planet would turn into a snowball. We need to retain some heat. But if somebody points to the geologic record and says, look here, carbon dioxide levels in the geologic record are going up, and the average temperature of the Earth is going up with it. What they don't tell you is, it isn't the carbon dioxide that occurs first, and then the heat that, the temperature that rises. It's the other way around. The temperature rises, and then the carbon dioxide goes up behind it. So there's a difference there in cause and effect. Carbon dioxide didn't cause the geologic history of the Earth to be hot or cold. It was a response to. Okay, so there's your greenhouse effect. You can look at it if you want to. There are different things that we could substitute for that produce less carbon dioxide. So if you're so inclined, coal gasification, take those large molecules that are in the coal beds and turn them into natural gas. And in the process, you remove a lot of the pollutants. You remove all the sulfur, you remove all the ash, and carbon dioxide, methane, when it burns, produces more energy per mole than the other products. Hydrogen, that's the holy grail of chemical power. If you can get a clean, plentiful source of hydrogen and the technology to use it, hydrogen fuel cell, for instance, you can convert hydrogen combined with oxygen in the atmosphere and make electricity directly. Feed it into your vehicle and run your electric motors and go motoring down the highway. The problem is twofold. Hydrogen is hazardous. How are you going to store hydrogen in your car and be safe in a car wreck? All they have to do is puncture your tank and the whole place goes up in flames like the Hindenburg. We're working on that. The other thing is fuel cells. They're not very efficient and they run at very, very high temperatures. That's coming down. The temperatures are coming down, but the space program that we had in the 60s was the moon rockets were dependent upon, those modules were dependent upon fuel cells. And they were very expensive to manufacture and they ran at high temperatures, so they had to take special precautions. Right? And any technology that you're going to dispense to the general public has to be idiot proof. Right? That's just a fact. And it's not there yet. What are energy alternatives? Oil shale. Fracking gets more oil out of shale. Same with natural gas. Fracking gets more natural gas. Right? If it wasn't for the Biden administration, we'd be producing, I think the estimate is 2 to 3 million barrels a day more oil than we're producing now. And several billion cubic feet of natural gas more per day than we're producing now. We're now an energy importer, whereas before Biden took office, we were energy exporters. And energy is power. We can keep all our enemies at bay by supplying ourselves and all of our friendlies with enough energy so they don't have to depend on their enemies, like Europe did with Russia. Now they're paying for it. By the way, when Trump went over there and told them what they were doing was suicide, they laughed at it. Ethanol. Ethanol, I remember ethanol was touted to be the salvation for our energy needs. Ethanol from corn or any kind of grain takes more energy to make a gallon of ethanol than it does to burn it. So it's a net energy loss. That industry, the ethanol production industry, would go out of business overnight if it were not for government subsidies. Methanol is another possibility, seed oils, solar. That includes both photovoltaics and wind. That's a dead end street. For one thing, the sources are very intermittent. We don't have storage technology to take the high production times, store that energy in some form that can be used efficiently when the sun's not shining and the wind's not blowing. Okay. They are also uncompetitive without subsidies. And the other thing is environmental hazards. People don't like to talk about it, but we make lots of hazardous waste when we make photovoltaics or generators for the wind turbines. That's on the front end, right? You generate a lot of hazardous waste, and then they only have a limited life, 10 to 20 years. What are you going to do with them? Dump them in your landfills? More hazardous waste. Nuclear is the only solution to all these questions right now. And I'm out of time, sorry. I was going to say some more, but I guess I can't.